hopefully all good. But yes, I'm Liina Chung-Jukko from King's College London, and I'm going to be telling you about the electromagnetic weight loss of axion stars. Most of my talk will be based on a paper recently published in PRD. It's called Electromagnetic Instability of Axion Stars. So from that, you might pick up that what I mean by an electromagnetic weight loss is an electromagnetic instability. So yeah, if you want to know more, please have a look at that paper after my talk. Now, if you're wondering why there's a Pac-Man in the middle of my slide, it might become a bit clearer to you in a couple of slides' time. But the main idea is, for the rest of my talk, the Pac-Man will represent my axion star. So wherever you see Pac-Man, I want you to think axion star. Great. Oh. So, well, we got a really nice presentation into the QCD axion in the previous talk. So that's great. I don't need to do that. But for the sake of my talk, the axion model I'm going to be using, you can think of it as some kind of axion-like particle model. But the key points are highlighted here on my slide. So I'm looking at a real scalar field with a finite mass m, and then it has a coupling to electromagnetism that I'm going to be denoting as GA gamma. Some people denote as a GA gamma gamma, but essentially it's the same. It's the thing that sets interaction strength between electromagnetism and my axion field. And what I'm interested in are these objects called axion stars, which obviously in the particle picture are just collections of these axion particles. And in the field picture, they belong to a class of objects called solitons. And more specifically, they're called, the model I'm looking at is called oscillaton. Now, an oscillaton has that name essentially because it's a stable field configuration, but it's oscillating, meaning the central field value, and I mean all the field values are basically oscillating. So if you look at, for example, at my field value in the center of this field configuration, it's going to be constantly oscillating, and you will see that later in a video, and that's kind of crucial for the phenomenon I'm going to show you that will happen to these axion stars. We also call it a self-gravitating compact object. And because I'm doing my work in the strong regime of gravity, basically what I mean by that, it's an energy packet held together by the competing forces of gravity, which wants to crush it, and the gradient energy, which wants to push it outwards. And hence, it's kind of this compact object, which is stable. Now, it obviously has finite mass, and more specifically, it's a time periodic solution to the Einstein-Klein-Gordon equation, where obviously the Einstein part is gravity and then the Klein-Gordon part is the scalar field. And I should probably mention that, for example, axion in string theory span a wide range of these values for small m, so the scalar mass and this EM coupling. And therefore, these stars could fit a wide range of axion-like particle models. And if you're wondering how we can form these kind of objects, if we want to look at compact stars, and I'm going to come soon to why I want to look specifically at compact stars and why my work is about compact stars, you essentially need some field fluctuations in the real universe that then will cause this collapse into these kind of stars. If you've worked or you know anything about primordial black holes, the formation mechanism is quite similar. And I'm not an expert on this formation mechanism for these stars, but I believe that Miguel's talk, which I think was just swapped, so it's going to be right after mine, will look at these kind of similar stars, but in the non-compact regime. So yeah, so if you want to look at the non-compact stuff, it's going to come later. So here's a plug for Miguel's talk. And I believe he's always also going to address the issue of formation in his talk. But what I'm really interested in is what happens when this kind of axion star interacts with electromagnetism, and how can it interact with it, and what can be the outcomes. So there's true primary decay channels that these axion stars can decay into photons. Axion can decay into photons in the first place. I probably should mention that there also is spontaneous decay, but that's quite slow for typical axion masses of less than 1 electron volt. So on the left of my slide, you can see the Primakov process. And most of you would probably be familiar with that in kind of one way or the other, but essentially many axion detection experiments are based on that. So that is just that in the presence of an external magnetic field, the axion becomes a photon. Now on the right-hand side, the formation mechanism, the decay mechanism that is key actually to my work is called parametric resonance. And here, the very basic idea, I can have the high school physics example of resonance where you have a bridge, and then when the wind happens to like be at the characteristic frequency of the bridge, then the bridge might collapse. So essentially, parametric resonance, you need an object that is resonating, and you need to drive a force. And in my case, the oscillator is actually the electromagnetic field or the resonating object. And it's the oscillation of the star that will then provide the driving force to get photons out of this electromagnetic field. And I'm going to come back to that in more detail, what I mean specifically. But if we look at parametric resonance in the context of the axion stars, that's the really basic idea. And yeah, I had to put this plot that let's see if it like shows up on every single presentation slide. But obviously, this is quite this plot in terms of the bounds on the axion mass compared to the coupling is quite key, because I am looking at the electromagnetic interaction of the axion of these axion stars. And I think on this plot in the left corner here, if you see my mouse, it's really small, so probably can't read, but it says axion star explosions. And I think this will be, this is where Miguel's talk will will explain to us where this bound comes from. So stay tuned for that. Great. So now there's one key thing that is important for my work, because what I essentially am doing is I'm simulating these axion stars in the strong regime using numerical relativity, as I'm going to come back to it soon. So that means that my axion stars are relativistic, they are compact, and they are solutions mentioned before to these Einstein-Klein-Gordon equations. So here's my paper that was recently published, also in this strong field section. And so this is different from the weak field regime, where the axion stars would be non-relativistic, non-compact, and often they would be solutions to Schrödinger-Poisson equations, so where people use some kind of Newtonian gravity. And I put this paper I left et al. From 2020. Some of you might know it. It's called Radio Emission of Axion Stars. And I put it there because, as a spoiler alert, what they did is that they looked at these non-compact stars in the weak field regime, but axion stars. And what they found is that if they put an electromagnetic field in addition to the star starts glowing, which essentially means that they found that the axion star started emitting photons because of this electromagnetic field. So this is kind of the spoiler alert for my work. So again, I have a slightly different type of axion star because I'm looking at the strong field, at this compact object. And for those of you that like been working with compact objects, the mass of the star goes roughly as mass Planck squared over the underlying scalar field mass. And that means that for a mass of around 10 to the minus 11 electron volts, the star mass is around 10 solar masses, which puts the gravitational waves from the star in the LIGO range. And if you go and look at my paper, this is the reason why we're using this 10 to the minus 11 electron volts as a reference mass. So I hope that now we're all on the same page about what are axion stars, why are they interesting, and which kind of tool I'm using, because I'm looking at the strong regime. So now let's get down to business. Here on this slide, you can see the action of my theory. So as you can see, I have the usual gravity term, I have the usual kinetic terms for the scalar field and for the field strength tensor. So just to recap here, in my action, phi is my axion field, so a scalar field, a real scalar field, and then F mu nu is the usual field strength tensor, so essentially representing the electromagnetic field. My axion is in the potential m squared phi squared potential, which in this case means that we're ignoring self interactions because we don't have the higher order terms. And the last term on this action is the most important one, because that's the coupling term. So you can see that there's the GA gamma, which is the coupling between the scalar field phi and the field strength tensor. So that sets the strength of the interaction. And you can see there's the phi, so the axion, and then there's the field strength tensor F mu nu. And what I'm essentially doing is I'm solving the classical equation of motions for macroscopic system of axions. And when you vary this action, what you get is the gravity sector equation of motions and the matter sector equation of motions. And the matter ones in this case are the most interesting, so I put them down here. The first one is the equation for the scalar field phi. But the second one is the equation of motion for my field strength tensor. And as you can see, it's essentially some kind of a source Maxwell equation. But the source term, you can see now, has two key ingredients. The first one, it has the field strength tensor, which means that classically, you need some kind of element field to excite photons from this system. But secondly, it has this derivative of phi, which means you need some kind of oscillating scalar wave or some kind of field gradients for, again, excite photons out of the system. And so this is why it's really important that, as I mentioned before, my star is a oscillaton, so it's an oscillating field configuration, because it's the oscillations of my star that will then drive photons out of my system. And as mentioned earlier, I am solving a system using numerical relativity. For those who are not familiar with that, that essentially means we solve GR on the computer. So we solve the whole thing with a fully nonlinear simulation, which includes basically all the back reactions. And if you want to have a picture of how that looks like in practice, in numerical relativity, we divide Einstein's four-dimensional space-time into a three-dimensional kind of spatial space, and then evolve that in one-dimensional time. So what my simulation actually have is I have a box, a three-dimensional box, my star is the center, and then I set this plane electromagnetic wave to model this electromagnetic seed. So essentially, I want to model some ambient radiation that the axion star might interact with in space. So like the energy density of my electromagnetic wave is much, much lower than that of my star. And then I start evolving this three-dimensional box in time and see what's happening for that. And the key question is, what happens when this stable axion star interacts with electromagnetic radiation in full GR? And when I say stable, I mean that if I turn the coupling to zero, so no interaction, the star just kind of keeps being there and nothing happens to it. Great. So essentially, what happens is this. Remember, I said wherever you see Pac-Man, think axion star. So now the little Pac-Man on the left is the star I start with. And as I told you before, I send this electromagnetic wave that I model as a plain electromagnetic wave going to my box, my simulation box. And now if you protest, because some people have, if you protest that, why is there a rainbow going to Pac-Man's mouth? It's essentially because, yes, the plain electromagnetic wave is just one frequency, but I tried many different frequencies to make sure that I just didn't somehow magically hit the magic frequency that makes something happen to the star. So yes, I tried different frequencies which are represented by this rainbow of color here. And so what happens is at some point, my axion star that was stable before, something happens to it and it dilutes and it increases. So basically its radius increases, but it loses a lot of mass and it becomes this big Pac-Man, you can see on the right of my slide. And how it becomes this big Pac-Man is essentially by emitting radiation, electromagnetic radiation at a single frequency. And what I'm claiming is that the frequency it emits this radiation is actually the characteristic frequency of the star. So it's something really inherent to the star happens, and it starts emitting this radiation at its characteristic frequency. Now, if you're not quite convinced about this representation of my physics, then what about this one? Before I play the video, on the left, what you can see is the energy density in the scalar field, so in my axion field. When I start playing the video, you see that the star starts oscillating because I told you it's an oscillating solution, so even the energy density will oscillate. On the right-hand side, you see the energy density in the electromagnetic field. And because I told you that I said it's such that it's much, much lower than the axion star energy density, for a while you won't see anything, but there's kind of this background going on that you can't see. But then at some point, the process I just showed you on the previous slide happens, and you will see a burst of electromagnetic energy coming from the star as it starts to decay. So let me just play it for you. So as you can see, On the left, I have a star that is kind of looks stable and it's kind of happily oscillating, and the electromagnetic field seems to be just doing its own thing and not caring. But then suddenly something happens, and the electromagnetic energy is strongly excited and it's strongly localized on the star. So you can kind of see that it's really like this, it's really the star that's emitting this burst of light. And then the process seems to stop. And I know that it's a bit hard to see on the left-hand side, but actually there is a remnant left. There is the big Pac-Man left that I showed you on the previous slide, but it's just the scaling works like that, you can't really see it. But essentially the electromagnetic energy density, the burst stops. So it's kind of back to this original setup. So let me play to it again. So we start with a stable star, which is oscillating nicely. But at some point, something happens, and the electromagnetic field will be strongly excited and localized on the star. If you're wondering why the oscillation is a bit asymmetric, that's because I'm setting a plane electromagnetic wave, which kind of chooses one direction and kind of breaks the symmetry of the system. Now, so what's happening? So what's happening is, I told you before, is parametric resonance. So in this case, again, you can think of it as the electromagnetic field being some kind of harmonic oscillator. And then the oscillation of my star is basically the driving force that will excite photons out of this harmonic oscillator. But there's something a bit deeper going on as well, which is it's well known that for just a homogeneous scalar field, axion scalar field, so forget for a while about the star, a homogeneous axion scalar field would have a resonant frequency band with electromagnetism that is set by the coupling between them, so GA gamma, essentially. That's what I plotted in yellow on this slide. But because I just don't have a homogeneous scalar field, what I have is a compact star, which sets a length scale. Now, this length scale will have a certain characteristic frequency, which is essentially roughly 1 over the length of the star. And what you saw happening in the previous video is that I started with a situation where the coupling was such that the length scale of my star corresponded to this resonant frequency band. And at that point, the parametric resonance process will start happening. So the process started happening, and the star started resonating with the electromagnetic field and exciting photons and losing mass. But as you can see, when the star started losing mass, its radius started increasing. And when its radius starts increasing, then the length scale also changes. And slowly the star shifts out of the frequency band. And when the length scale of the new kind of star, which is much like the radius larger, is not corresponding to this resonant frequency band anymore, parametric resonance stops. And I'm left with a remnant star that can't resonate with the magnetic field anymore. So this is kind of the physics that is happening behind the scenes in the video that I just showed you. Next, this is a third representation of this parametric resonance process and what's going on. So here, what you can see is for 3 different values of the coupling. On the solid line is the total energy in my scalar field, so it's essentially the total energy of the axion star. And the dashed line is the total energy in my simulation box, I should say, in the electromagnetic field. So as you can see, I started with an energy in the electromagnetic field that is much, much smaller than the scalar energy, and both of them kind of are stable for a while until parametric resonance kicks in, and suddenly the scalar energy just drops rapidly when the star loses mass and like dilutes, and the electromagnetic energy is shoots up because basically the star is emitting these photons. Now, this is all well for, you can see the blue line, so for coupling 16 and for the coupling 14. As you can see, when the coupling becomes smaller, it takes more time for this process to start, but also the process kind of takes longer and doesn't extract as much energy from a star, which makes sense because a stronger coupling means that the interaction is weaker. But then you can see that there's this black line for coupling 10 where nothing seems to happen, which means my little Pac-Man just keeps being little Pac-Man and never dilutes into my big Pac-Man. So what's going on in here? This made us think that there seems to be a critical coupling below which we can't see the decay of the star. And if you think about this resonant frequency band I just showed you in the previous slide, that makes sense, right? Because essentially what it means is that when a coupling is such that the resonant frequency band is away from the length scale of the star, kind of I start with a situation when the length of the star is away from the frequency band and I can't see any parametric resonance happening. So now all and well, you might ask, oh, but you've done this only for one mass. What if I just happen to pick the magic mass where everything works out? Well, we decided to do some more experiments. So on this slide, what you can see is each column of points corresponds to one, a different mass of a star. So we kind of repeated these simulations for 4 different star masses. And as you can see, there for some simulations, when we change the coupling, so I think when I say change the coupling, essentially what you should think about is that I'm making an experiment where I'm simulating a parallel universe where the coupling between electromagnetism and the axion star is different. So each point is kind of a different universe with a different coupling in some sense. As you can see, for each star mass, there seems to be a critical value above which the star will decay and below which the star will stay stable. And honestly, what these results mean is that the existence of pristine compact axion stars is actually strongly restricted by their coupling to electromagnetism. Because if I happen to form somewhere in the universe, if I happen to form a star whose coupling, whose critical coupling is below the actual coupling set by the universe, then it would actually decay. And here you might say, okay, but like, how quickly do these things actually decay? And so we did this base calculations where we integrated over the CMB power spectrum, and we kind of integrated over the CMB over the frequency range that is roughly near this star range. And by integrating and taking into account the energy in each frequency, we find out that this process should happen in less than a minute. So obviously on cosmological timescales, the existence of these stars should be strongly restricted. And so I have just a couple of slides left. So that's my next few slides will be based on unpublished work. So it's something we're working on at the moment with my supervisors. So the thing you might ask now is, what about mergers? So what about if I start with 2 axion stars that are stable on their own, so they don't decay, but then they merge and they form this blob, which suddenly has the potential to decay. So what happens? So let me just show you quickly what happens. So this is the same kind of thing as in the previous, where you can see the axion stars on the left and then they merge, and then suddenly this thing that is created has the potential to now decay. And now you can see parametric resonance starting. You can see the strong burst in the electric field on the right, and the thing that merged decays strongly. So let me show you it quickly again. So on the left, you see my 2 stars. They will merge. They are stable on their own, but now they merge and they produce this highly excited blob. That's why it's kind of oscillating a bit, because it's highly excited due to the merger. But now this one has a different critical coupling, and hence it can decay through parametric resonance, as you can see on the right. And on my final slide, before wrapping up, oops, okay, let's see for the 3rd time. You can see the gravitational waves, if you're interested in gravitational waves. So this is the gravitational wave from the process of merger and decay. So the first, here on the real part, the first thing, that's the merger signal. It doesn't have an imaginary counterpart because it's a highly symmetric situation where I have only one of the modes excited. But then you can see that the decay actually has a gravitational counterpart, which is really strong. And it's a preliminary result that actually it seems that this decay has 10 times more energy in gravitational waves than the merger. So yeah, that's an interesting result. And we're in the process of seeing how we can map this to LIGO and whether like this could be potential for having some templates out of this, because the merger and the decay have some really clear distinct signatures. So I'm going to leave you with this take-home message. Yeah, I'll just take if there's any questions.
Thanks a lot. It's very interesting and new idea. So yeah, we're open to questions now, if there is any. If not, I have a couple of questions. I would like to ask, do you expect multi-messenger, or in general, do you expect the electromagnetic signal to be picked up?
That's really good question. So I think in terms of looking at whether this EM signal could be picked up, there's a lot of astrophysics consideration to be had in terms of, for example, can the Electromagnetic signal escape the wherever it is, like the matter cluster where it is, and so forth. So we haven't done exact calculation of that, but I know that that has been done in the context of non-compact stars. So I think, I'm not sure, Miguel might talk about that. And then my supervisor, Dodi Marsh, has definitely, I think, been looking at this for non-compact stars and looking at the mergers and then the energy injection into the intergalactic medium. Yeah.
Okay, let's see. But another question I have is this star in the dilute branch? In this branch in which you have quantum pressure counterbalanced by gravity, like you don't take into account the self-interaction of the axion. Is it the branch where you're at?
Yes, exactly. So I don't have self-interactions because I only have the quadratic potential. Yeah, that's correct.
Okay, thank you. Okay, any more questions? If not, we hear the rest of the story and we thank Liina again.
We had question from, I think, Miguel and Malte. They raised their hand, right? No? No? Sorry. So I got confused. Well, I have a question.
No worries. Sure, yeah.
So thanks for the nice talk. So did you consider gravitational redshift or blueshift for the photons that are emitted? Because if you have this parametric resonance, right? When one photon is produced, it's kind of stimulate the production of other photons. But if it's shifted in frequency, it will not do it anymore, right? So yeah, I just wonder if you consider that effect.
Yeah, that's a good question. No, the short answer is no. We didn't consider that effect. But but essentially, as I mentioned before, we tried different kind of seed frequencies, and turns out that even if the seed frequency is kind of away from the characteristic frequency of the star, it will just take longer, but the parametric resonance will start at some point. So yeah.
Yeah, because like you were working in the like strong field limit, right?
Exactly.
You said.
Yeah.
So I will expect that the gravitational effect on the photons will be higher.
Will be yeah. No, we didn't look at that individual thing. I think one thing is our results are actually quite close to the result from the paper in Levkov et al., where they look at the weak regime. I mean, there is a difference. Like, I think where like from the critical coupling is off by a factor of like 8. And so that just means that like this process is quite strongly driven by the matter couplings, even though gravity does play a role. Yeah.
Okay.
I think David Marsh has something to say.
Yeah.
Thanks for that. Yeah, I just wanted to add the gravitational redshift, because what Liina's done is in full numerical GR. The gravitational redshift should be automatically included. In GR, I mean, all the back reaction terms are there. You're solving Einstein's equations with electromagnetism. So any redshifting is automatically included.
Because
that should be